Good morning, everyone. My name is Dave Cooper. I'm one of the trustees of the Symposium, the educational trust that runs today. I can't believe this is the 15th time we've run this. I was just thinking it's back in about 2010. First one was 2011, I think, wasn't it? So a load of young, keen lift engineers got together to get a symposium together, and now the same old lift engineers are still running it. But so very much a big welcome to the 15th meeting, and it's great to see so many people here. I mentioned the trust and the trustees earlier. I cannot say how grateful I am to all of the trustees and the organising team for getting this together. It is a lot of hard work, as you know, and it's really superb. There is a fire alarm at 9:45, but don't worry about it. It literally is a test, and it's ironic that it's in the paper about alarms. I'd also like to thank the exhibitors at the back of the room. Do please go and visit them during your coffee breaks. It's lovely to have you here. Lovely. It really is good, and the exhibitors really help us get the ball rolling every year. Obviously, we need to bankroll the event, and it's superb to have the exhibitors with us. So, I'm chairing the first session. And we have 4 papers on IoT and technology. Our first speaker is Rory Smith. I don't think Rory needs any introduction at all. But Rory is a visiting professor in engineering and lift engineering at the University of Northampton and a consultant at Peters Research Limited. He has over 55 years of lift industry experience, during which he's held positions in research and development, manufacturing, installation, service, modernisation and sales. His area of special interest are machine learning, traffic analysis, dispatching algorithms and ride quality. And he's had numerous patents awarded for his work. So without further ado, Rory.
Okay, so today I'd like to talk a little bit about some new technologies that can improve escalator safety. I've always viewed escalators as not being so safe, and I think that kind of is well-founded, but there are some new technologies that do make them quite a bit safer if they're implemented. And so I'd like to just talk a little bit about that and about safety in general. There's a lot of escalator accidents, and they fall into a couple of 2 different categories. One of them is falls, and the other is entrapments. And there's other forms of accidents, but these are largely the accidents that we see happening. So falls are typically the typical victim in a fall tends to be someone over 65 years old. As people get older, they have less cognitive ability, at least. Maybe the President of the United States is a good example of that. And I hope it doesn't happen to me. The other characteristic tends to be that they are females. And it's like 2/3 of the fall accidents victims are women. And not sure why. I've tried to research that. There is an age, there's a gender gap in age of how long people live. That's going down. But that's just the way it is. Most people are carrying luggage, and so you get on the escalator. You're carrying luggage, maybe in both hands, and then the steps separate, and you fall backwards or forward, depending on which direction. For a number of years, I was responsible for all of the lifts and escalators at the Dubai airport, and I would get a video every time there was an accident, because we had cameras at both ends. And the typical accident was somebody had a carry-on suitcase and a bag that said Dubai duty free. So both hands were occupied, and then they would fall. So luggage is a big factor. And so falls tend to occur in 2 different locations. Primarily, it's while boarding, and they occur at where the step transition goes from level to where the steps rise. So they happen at both ends. Most often at the lower end, from what I've been able to observe. So as they get on, the steps start moving, and people have a difficulty transitioning from walking to stepping onto a moving step. And so then with entrapments, it's a little different typical passenger. With entrapments, you have the typical victims are children, and they tend to be wearing high coefficient of friction footwear, and particularly Crocs. And Crocs were originally designed as a boat shoe, so you wouldn't slip on the boat decks. And they have very high coefficient of friction, like 1.8. I mean, it's really, people don't think you can get more than 1, but you can with coefficient of friction, and that's really high. And near misses are largely unreported. So if you talk to somebody who works on escalators, like my son does, I don't know what's wrong with him, why he wants to work on escalators, but he loves it. And he says every time they clean the pits and clean the pans underneath, there's always pieces of Crocs and other footwear. So I suspect a lot of people exit an escalator minus 1 shoe, but it could be worse, because many people exit minus a toe. So these are the typical people with entrapments. The location for entrapments tends to be, there's like 3 different locations. There's between the step and the skirt, there's the step risers, and the comb plate. So those are the 3. Now, the injuries tend to be usually minor. However, until the entrapped body part impacts the comb plate. And that's where the real injury takes place. And so if you can avoid getting your foot, it's not going to be pleasant to be trapped and slid down the escalator to the comb plate, but if the escalator comes to a stop before you get to the comb plate, the injuries tend to be minor. Meaning there's no amputations of toes or bones and fingers when you get to if you can avoid impact with the comb plate. So how can we improve safety on escalators? Well, let's take a look at some fundamentals of safety. Safety is the freedom from unacceptable risk. That's what we're trying to do. And safety is achieved by risk assessment and with risk reduction. And there's an ISO standard for this, and that's this one right here, 14798. It is a ISO standard on how to conduct risk assessment for lifts and escalators. It's a very good guideline on what to use. It's the standard we're supposed to be using in the industry. I think it's a good standard. I will talk about how to make that a little better on my subsequent lecture this morning. There's some important definitions that we need to understand. Most of you are familiar with these, but I'll just go through them, a refresher. Hazards are a potential source of harm. And harm is physical injury or damage to the health of people, but also property and the environment. So we really need to look at all 3 of these when we're thinking about risk assessment. Risk is a combination of two factors, and one of them is the probability of the occurrence of the harm, and the second is the severity of the harm. So if you have something that is a type of harm that could be, let's say, fatal, let's say a meteor striking you, okay, that's definitely going to be severe, but the probability of it occurring is pretty remote, so there's no real market for portable meteor detecting devices. We don't need them. But there are other things where we have very high probabilities of harm, and that's where we have to work on it. So this ISO standard addresses that. And so risk assessment is a methodology to identify the risk and the harm resulting from a hazard. How many of you have done risk assessment before? So quite a few. Okay, so you're familiar with all of this. So just a little refresher. So how do we reduce falls? Well, the one thing that can really reduce the amount of falls is our variable speed drives. Now, previously, escalators ran at either 1 or 2 speeds, and they had like across the line or star delta starting, or they could run at a slower speed when there was no activity. But now they're available with variable speed drives, VVF drives, similar to what you have on most lift machines today. And the variable speed drives can reduce the probability of occurrence of falls. Now, how do they do that? A number of different ways. Variable speed drives reduce falls by brake failure reduction. Now, brake failure is a major problem on escalators because most of them are strictly a mechanical brake that applies. So how do you stop the steps from moving? You apply a friction brake. And of course, the more times you apply that, the less brake material there is available to stop the lift. However, with a variable speed drive, you can reduce the harsh stops because you're using you can also dynamically change the velocity. So I'll talk a little bit more about each of these, but you can change the velocity of the steps based upon for congestion control. Where congestion is where you have a bunch of people accumulating at the exit to the escalator, and the following people coming down the escalator or up the escalator can't get off because there's people in front of them. You could using cameras. You could slow them down. And you can also operate them at reduced speed. And there's some really good research in that area. So dynamic braking stops the steps electrically. Just like a lift is stopped electrically rather than using brakes, you can just bring the escalator to a controlled stop. And the mechanical brake then just becomes a holding brake. It holds the lift stopped. So it doesn't wear. Brake wear is almost completely eliminated, just as it is on like gearless machines or geared machines. There's almost no brake wear. Previously, when we had single-speed and two-speed AC machines, that they were stopped on the brake. And I remember taking brake shoes to a brake shop to have them relined and arced, and that almost doesn't happen anymore. And the same would be true with escalator brakes. So they will be there when you need them because they were being dynamically braked. And the ASME A17 code says if you have dynamic braking, you don't need an auxiliary brake when the travel is more than 6 meters. I think the ASME code is actually promoting dynamic braking by the way they've modified their code. No harsh stops. Well, harsh stops cause falls. And when you get a mechanical brake stop, people fall not because of getting on or getting off, just the stop is so harsh, it creates a fall. And it can be a cascading fall where one person falls on the person ahead of them and you get that. But if you have a closed loop system, with feedback, your stopping distance is always the same, whether the escalator is going up or the escalator is going down, whether it's fully loaded, whether it's empty, you always get the same performance. And then because the stopping distance is always the same, you can reduce the deceleration rate and the jerk rate can be reduced. Particularly jerk rate contributes to the falls. So jerk is a change in the rate of acceleration. So with these dynamic brakes, you can have a very long. You can use the maximum distance to slow down. I think the 115 code says the maximum negative acceleration rate or deceleration rate is 1 meter per second squared, and the ASME code says 0.9. Lower is better because the jerk rate can then be better, and so it makes it a safer escalator. And then dynamic velocity control. So we can vary the velocity at low acceleration and jerk rates even when the escalator is occupied. Now that's not something that's readily available in any code or even really addressed. But imagine that you wanted to accelerate or decelerate. If the acceleration rate is slow enough and the jerk rate is slow enough, you won't even know it's happening, but it can be done. And you can reduce the velocity during reduced traffic periods. So there was a really interesting study done by the Guangzhou Metro in China, where they found that the majority of their accidents occurred during off-peak hours, not during the morning rush hour or evening rush hour. And at first you say, well, that doesn't make sense because you would think with a lot of traffic. But the people that were rushing to work were young. They were working people. And the retired people or the people that are tending to children would be taking the metro at off hours. And so one of the suggestions they came up with, well, there's less traffic, there's less demand for vertical transportation. Why don't we just slow down the escalator during this off period? Makes it easier for people to step on and off the steps. And I think this is a really good concept. The other thing you should remember is that in the 115 code, the maximum speed is 0.75 meters per second. And in the ASME code, it's 0.5. But there's even been studies by the Federal Aviation Administration, who controls all the aircraft and airports in the United States. They're saying, make it slower than that. There'll be less accidents at airports for falls if you go slower. So I'm not sure what the right speed is. Certainly you can't reduce the speed at some of the London Underground stations because they're so heavily trafficked. But you could reduce them when the rush hour is not there. And the only savings you have is energy, really. There's no loss of traffic handling because there's no traffic to handle. So something to consider, that you can do this very easily if you have a variable frequency drive where you can just change the speed at will. And you can also reduce the velocity when the exit is congested. Now, how could you do that? Well, you can very easily do that with cameras and AI, where you can see that there's people accumulating near the exit. You could then slow down the entry of people onto the escalator, and you can't do it really rapidly, but any reduction helps the congestion to clear because the input of people at the exit is less. So this is something that could now be done just naturally because you have the ability to vary the speed based upon AI. Entrapment, it's possible to address the probability of occurrence. How do you do that? And that's with the ASME code, they require something called the skirt step index performance index, and it measures the gap between the skirt and the step, but under load. Now the step band, which is the entire belt of all of the steps, can move. It has a dead zone that moves back and forth very slightly, but when you put it under load, the gap gets larger. So this test measures the gap when it's under load, which is a more aggressive way to look at it. And the maximum gap is, I think it's 5 millimeters, whereas in the 115 code, it's 4 millimeters on each side and a maximum of 7. This is a more aggressive way of doing this. And so that you have to measure this, and you have to measure it every year. And it means the skirts have to be adjusted every year because they get out of alignment. So it measures and it also measures the coefficient of friction of the skirt. So we're worried about entrapping clogs and crocs. This way we're addressing this. Just cleaning the skirts reduces the coefficient of friction. But we've all seen a lot of skirts that are all scratched because they've been scratched by the steps. And so it requires, sometimes you have to polish out the scratches, and then you have a different coefficient of friction, or a different traction value, really. And then this reduces the probability of occurrence. So if there's no gap, there's no way to get your foot in the gap, and so there's no way to get your foot entrapped. So if you control the gap, you reduce the probability of occurrence. There's also how do you measure this? Well, there's a skirt step performance index, and it requires a machine like this that actually puts a force onto the steps, and you can then measure this under load, and it measures the coefficient of friction of the skirt, and it measures the gap, and it does a mathematical calculation that says that you have a factor of, let's say, 0.25. If you have to get below 0.25, and if you get below 0.25, if you're between 1.15 and 0.25, you need brushes. If you get below 0.15, you don't need brushes in the ASME world. Brushes are always a good idea, and but they're not this gives a more dynamic thing, so it reduces this. But it requires a special tool, and there's only one company that makes these tools, as far as I know, PMT, who also makes the ride quality analyzers that a lot of people use. So special tool, but probably worth it. Probably worth the effort. And then this reduces the probability of occurrence, but we can also reduce the severity of harm. And the severity of harm can be done by skirt obstruction devices. What's a skirt obstruction device? Well, it's a skirt switch, not required in 115, but required elsewhere. And so it detects objects that are entrapped in the skirt, and they're located where if they detect an object, they bring the step band to a stop before the entrapped body part hits the comb plate. So in doing that, you may not have kept the accident from occurring, but you've kept it not being particularly bad because you stopped the person. They're trapped, but they haven't hit the comb plate. They haven't lost their toes. They haven't been really badly injured. So this reduces the severity of harm, and this is required in Canada. It's required in Hong Kong by EMSD, and it's required in USA. Now, in Hong Kong, they also require skirt switches along the path of the escalator. So every so many meters of rise, they require an additional switch. People don't like skirts. Lift and escalator people don't like skirt switches because they do have false activations. But you have to weigh, well, what's a false activation versus a false foot? And I think it's a pretty good bargain to put the switches in. So they're required in these places. There's another device that reduces entrapment, and that's the step upthrust device. Not required in 115, but required in ASME. And it's similar to a step level device. A step level device measures if the step is below a certain distance from normal. Improperly called in much of the industry the fat lady switch, but it's not gender specific. It's just if the heavy enough load or misalignment, it stops it, and even in 115, it stops the step band before you get to the comb plate. So you eliminate the big injury. Well, an upthrust device does the same thing. It just in case one step, if the flip-flop pushes the step down, well then the step level device will detect it. But if it pushes a step up, then the upthrust will stop the step band before it gets to the comb plate. So it reduces step pileups as well. Now it's kind of interesting. Step pileups are a bad thing because the steps hit the comb plate, they pile up, the steps get so damaged, have to be replaced. Lifters down, escalators down for a while. And it's interesting that one of the largest multinationals, if you go to their Singapore website, they're offering upgrade kits to add skirt switches and upthrust switches. So there's a recognition that they have some value. So if you figure out who the non-Asian multinationals are, go look at the websites for Singapore. You'll find these adverts there. So I guess we know it's a problem. So conclusions from all of this: I think closed loop variable speed drives can perform the following functions: dynamic braking, step velocity based on traffic level, velocity reduction when congestion occurs. And then I think it would be good to incorporate certain sections of the ASME code into the EN 115.1 code, and that would be the loaded gap step. These are specific sections that relate to the loaded gap, the skirt performance index, escalator obstruction devices, and step upthrust devices. And also consider limiting the speed on new installations to the 0.5 meter per second. A lot of research was done, I think it's by the University of Portsmouth here in the UK, where they looked at older people, the effect of older people getting on a moving step, and it's a real challenge because of their cognitive ability is not quite as good as it was when they're younger, and so lowering the speed makes the challenge of stepping onto the switch a little easier. So, and then consider using the escalator driving machine brake, again, the dynamic braking, rather than using the mechanical brake. So, questions?
Brilliant. Thank you, Rory. Len. Sorry, I'm doubling up here.
Yeah, sorry, my name's Len Housey, formerly from Canary Wharf. Rory, two things. Some years ago, Otis introduced an escalator called the Next Step Escalator.
Yes.
Which had an integral skirt band, integral with the step. Now, I don't know if there's been any developments on that and the proposal, but that would certainly be a big step forward in reducing the level of entrapments.
Yeah.
And the second question is, in terms of transition, if you look at what London Underground do, they have 4 and 5 step transitions.
Right.
So 4 at the top, four at the bottom and 5 at the top. Would that be an assistance in terms of reducing the level of,
absolutely.
Of accidents?
There's been a lot of research in that area that says that does give you more time to get your feet off of the yellow parts of the step. Because when you get on, you may be straddling 2 steps. But you have longer time then to move your feet and get to where you're not stepping on any of the yellow parts in the perimeter. The Otis step I thought was a brilliant idea. I don't know why it wasn't successful, but a lot of people now on the demarcation strips at the edge, they're plastic, they actually step up a little bit. And it makes it less comfortable to stand there, and so you're more likely to pull your feet in. I think that's a good maneuver, a good thing for everything. And it doesn't require the radical redesign of your whole escalator, because when you have the skirt, this part of the step like this, you have to make arrangements for it all the way around the step band. So I think it's a simpler modification.